All right, so yesterday we had our brief introduction to chemistry. We said that chemistry has kind of evolved through history. It started out as alchemy, people trying to make gold from other elements. Didn't work out very well, but we learned a lot through that process, and it developed into its own field. It wasn't until about 1661 where Robert Boyle started describing chemistry in its modern form. And he described it as matter being made up of atoms or clusters of atoms, and he described them as being in motion somehow. And I told you yesterday that chemistry is involved in a large number of fields. And then we briefly described the scientific method. This is one of the most important things you can take away from this course is the process through which you go through science, right? So you first make an observation, then you develop a question about that observation, then you develop a hypothesis. What's a hypothesis again? Anybody remember? Yeah, an educated, testable guess. And then we test that guess, and then we gather data regarding it, and then we might need to refine it, alter it, expand it, or reject it, and then we go into this loop, and eventually we gather enough data to develop a theory, ideally. That's the ideal endpoint in science. And what's a theory? Who wants to help me out with that? It's an explanation, right? So a lot of people mix up theories and laws, and that was one of the things we talked about. Is a theory explains the why, a law doesn't. A law just says this is what it is. And often it's a mathematical formula. So that's a good way of distinguishing the two. All right, and then really quickly we started talking about critical thinking in science. And this is a big deal, especially with social media and a lot of, quote, fake news going around. You have to be very critical of what you see and read. The first thing is when you're doing science, you first have to have a conceivable way of your claim being false. Then your claim needs to be supported by logic, it needs to be reproducible, and you need to have sufficient evidence. And this is the big one that I like to really push, is if you're making a claim, the burden of proof is on you, and correlation is not causation. So you really have to come up with some sort of causal relationship between two things. All right, so let's switch gears. And today we're going to talk about physical properties. And physical properties are important in science, and you'll actually talk about these during lab tomorrow. But they are things that can be measured or observed. Without changing one type of matter into a new type of matter. All right, so physical properties are pretty important when you're doing science. Let's try to come up with a bunch of different things that we can measure in science. So does anybody have a variable that you can measure without changing something? Weight, okay. So oftentimes scientists will use mass instead of weight, and we'll talk about that in a second, but really the same idea, right? So how heavy something is. All right, what's something else? So I know they do this in the doctor's office. What else do they do?
Oh, fluid, like fluid measurements and stuff?
Yeah, so you can do volume. Volume's a really important one, so that's how much area something takes up, right? So maybe you have a liter of water, you can measure that as being a liter, right? What else?
So would poop be mass?
So it depends how you're measuring poop. Are you weighing it, or are you looking at how much volume it takes? You could do either, I suppose. What else could we measure? Think about like around your house doing construction work. Height or length, yeah? So it really depends whether you're measuring something up and down or vertical or the application. Yep.
Temperature?
Temperature, absolutely. So let's say you have a cup of water, you can measure how warm or cold it is with the thermometer. What's something else? What do you think? Density? Yeah, absolutely. So for example, you could have a cube of styrofoam in one hand and a cube of lead in the other. They're going to be very different, right? We'll talk more about density in a little bit. Anything else? What do you think?
The state of matter.
State of matter? Yeah, we can start describing that. We actually have a variety of ways of describing state of matter. So let's talk about that. One thing we can measure is boiling point. That basically means how hot does something need to be before it starts boiling. So water boils at about 100 degrees Celsius versus something like methane actually boils below freezing for us. So we have to look at boiling point. In addition to that, we can look at freezing point, meaning how cold something has to be before it changes into a solid, right? So we can measure those things as well. So this kind of can be used to look at state of matter. So you're exactly right. We can also look at things like hardness. This one's a little bit abstract. Does anybody know what the hardest substance is on our planet? What was that? Diamond, absolutely. In fact, the only way to cut a diamond is with other diamonds. It's kind of weird. The diamond industry is pretty fascinating. We can actually make artificial diamonds, which a lot of people don't know about. So it's something you can always look up, especially if you're interested in ethical diamonds, where they're not mined in any foreign countries. All right. Another one you can actually measure without changing things is odor. Scientists have ways of measuring odor. So you can go around with a little meter and pick up specific odors. You can also measure color using special types of equipment. I know with human beings it's very abstract to define color, but we actually have instruments that will tell you the exact color of something. Yep.
So wouldn't that be like that spectrum thing or whatever?
The which thing?
Like the spectrum, like light, is that for lighting only, or is that, could you measure that color?
Yeah, color is actually very complicated. So not only can you look at color on the spectrum of visible light, but you can look at color intensity as well. So if you go into a field in art, that's a really big deal, is having the right color, the right intensity at the right hue, and that gets very complicated. Unfortunately, way outside of the scope of this course. But all of these are things we can look at without changing something, right? We can measure these, we can record data, we can put that in our lab notebook. So all of these are important things to include anytime you're doing experiments. However, there's a few of these I want to go back and talk about. The first one is, let me change this, is mass. That's pretty important. You're going to be looking at that tomorrow in lab. Next one's going to be volume. So we'll talk about that. And then we'll also talk about density as well. All three of these are going to be looked at in lab tomorrow. So I did want to go over those in a little bit more detail. All right, so let's look at mass and compare that to weight. It's very confusing because the terms are often used interchangeably. Mass is the preferred unit when we're describing physical property, or preferred term, I should say. And it is an intrinsic property. What do I mean by intrinsic? What do you think?
Regardless of context, it stays the same.
Yeah, regardless of context, it stays the same, right? Versus weight, if I'm in outer space, what do I weigh? I weigh nothing. So I have the same mass in outer space, but I weigh nothing, right? So weight depends on the environment that you're in. Are you in outer space? Are you on Mars? Are you on Earth? Are you on the moon? It depends a lot. So scientists don't like using weight because of that. Weight depends on gravity. So gravity is a very, very odd concept, but the easiest thing to remember is if you bound on the moon, you're a lot lighter, right? Or if you're in outer space, you're weightless. So we've got to look at how mass is measured. And it kind of bugs me because we're Americans, or at least we're in America, I should say. And Americans are incredibly stubborn people, and we don't like to follow what the rest of the world does. How do we measure our mass in the US? If you go to the doctor's office, what do they normally tell you your weight or mass is? Pounds, right? So in the US, we measure mass in pounds. However, everyone else doesn't. What does the rest of the world measure mass in? Kilograms or grams, right? It kind of depends on the context, but they'll use one or the other. So one option could be measuring something in grams, and the symbol for grams is lowercase g, or they measure something in kilograms. And the symbol for that is lowercase k, lowercase g. The difference between these is subtle but important. A kilogram is 1,000 grams, and we'll talk about what those prefixes mean, and I'll walk you through the process of going through all the different prefixes in science. One thing I like to do is, anytime I present a unit, is give you something that you can relate it to pretty quickly. So what I like to do is come up with some household object. So one example would be 1 cube of sugar is about 4 grams, give or take. So it gives you a rough idea. If you're holding a cube of sugar, that weighs about 4 grams. So it gives you a ballpark idea of mass.
Wait, just to make sure you said 1,000 kilograms is in grams.
1,000 grams is a kilogram, and we'll go over that a lot. It's very confusing. It's easy to flip-flop. But lucky for you guys, I made a cheat sheet for you that you'll be able to use in exams and quizzes. So you'll be able to use that as a tool. Okay, so let's switch to volume. That's the other thing you're going to be looking at tomorrow. Volume, like we said, is the amount of area that something takes up, or alternatively, we can measure it another way. It is the amount of area that you displace. So commonly what you do in a lab setting is, let's say you've got this big hollow tube. This is called a graduated cylinder. You'll have these in lab. And what it might have is a bunch of marks on it going all the way up. So maybe this is 10, 20, 30, 40. And let's say your liquid's at about 20 milliliters in here. And then what you can do is you can throw in some sort of big rock over here. And the rock isn't uniform. It's not something that can be measured because maybe its shape is inconsistent. And so now you look at your liquid container. The hash marks are still where they were. So I'll say 40, 30, 20, 10. But this time, your liquid goes up to 30, and your rock's now in the bottom of your liquid. What do you think the volume of that rock is?
10, whatever.
Yeah, 10 milliliters, assuming these hash marks represent milliliters, right? So in lab, what you'll do tomorrow is you'll toss pennies into a thing of water. You'll measure before and after, subtract the two, and that will tell you the volume being displaced, right? That's also the volume of the object. So we've got a few different ways of measuring this. Like I said, oftentimes chemists will use milliliters. And the symbol for milliliters is lowercase m and usually a capital L. However, sometimes you'll see it in a lowercase l as well. And usually this is the unit that's used for liquids. So does anybody have a water bottle? I think I see a water bottle over there. If you look at it on the label, normally you can see it's probably, what, 500 milliliters? Check. Yeah, exactly. So normally when you buy a soda, it's like 355 milliliters. A water bottle is about 500 milliliters. That's what we measure the volume of most liquids in. For solids, it can be a little bit different. You can measure solids in milliliters. However, quite often, what you used is centimeters cubed. So if you're familiar with math, it basically means you measure something lengthwise and you raise it to the third power. And you use this often for solids. So if you're looking at a solid object and you want to describe its volume, you can describe it this way. And I'll describe what that exponent means. So imagine you've got a cube, looks like this, cubes are three-dimensional. So we've got that. And you get a little ruler out, and you could say, all right, its height is 1 centimeter. Its width is 1 centimeter. And its depth is 1 centimeter. This is equal to 1 centimeter cubed. So it's all three of these components multiplied by each other, and that will give you the total volume. The other interesting thing is, just to make things more complicated, hospitals will sometimes use a different measurement. Instead of using milliliters, they use something called a cc. How many of you have heard of that from TV shows? Yeah, like if you watch ER or something like that, they talk about cc's of fluid. 1 centimeter cubed is shorthand for 1 cc. So you can use them interchangeably depending on the setting. If you're in a hospital, you describe it as a cc. It's the exact same thing as a centimeter cubed. So when we look at this, it's a little bit confusing, but also easy at the same time. We've got 1 centimeter cubed, that's what we often measure solids in, is equal to 1 milliliter, is equal to 1 cc, which is really just the same thing as a cubic centimeter. It's just a different way of writing it. So all three of these can be used to describe volume. Like I said, chemists, for the most part, really like using milliliters. It's just a lot easier than measuring things in any other way. So I'll just write preferred. Is there 2 R's? I'm terrible at spelling. Is that right? Preferred by chemists. They won't let me teach English here, only chemistry. All right, does that make sense? I know a lot of this might be review for some people, but it might be new for others, so we'll go over it. All right, so switching gears to the other topic that we mentioned we can measure is density. Density is a little bit abstract. Density is a unit that is mass divided by volume. And what sometimes people do is they abbreviate all of this. So they say density can be abbreviated as D, and mass can be abbreviated by M, and volume by V. Really, that's just our mathematical notation instead of writing it all out, right? The units are important. What's the unit going to be for density given what we just talked about? What's the unit for mass again? So in the US we use pounds, everywhere else they don't. What's the one unit?
Kilograms?
Yep, so kilograms. Chemists often will use grams just because we're not measuring super large things. If you talk to a physicist, they'll say kilograms. So it does depend on the context. But chemists often prefer grams. And like I said, for volume, chemists often like to use milliliters, right? So we've got grams over milliliters. Or if you're a chemist, you can use grams over centimeters cubed. So these are the traditional units for density that are used in a chemistry lab setting. The weird thing with this is if we look back at this mathematical formula, we can manipulate it and move it around a bunch, right? So I said that density equals mass over volume. That's one way of writing it. What would mass be equal to then if we're going to move these variables around?
Density divided by volume?
Close. If we want to get rid of this volume, we multiply both sides by volume. So it'd be density times volume, right? So mass equals density times volume. So let's say you know the density of something and the volume of something, you can extrapolate its mass. All right, what about volume? It'd be mass over density. So you can use this in a variety of ways to solve problems in a lab setting, depending on what you're trying to solve and which variables you have. You have to have 2 of the 3 variables, though. That's the important thing. All right. So let's take a look at some common examples. Like I said, I always like having some real world reference whenever I'm doing this stuff. So what's the density of water at room temp? Does anybody know what this one is?
Is it 6? I don't know.
I like this one because it's easy to remember. It's just 1. So it's 1.00 grams per milliliter. So oftentimes you can see it written this way, where you have the slash, or what you might see is 1.00 grams over milliliters. You're welcome to write it however you want. It doesn't really matter to me. It means the exact same thing. So you can write a fraction either on top of the denominator or with that slash. Okay, so the density of water is 1 gram per milliliter at room temperature. Why do you think I wrote at room temperature there? What do you think?
You mentioned earlier that matter is made out of atoms in motion.
Mm-hmm.
When you heat them up, they move more, so the density decreases.
Yeah.
They get larger.
Exactly. So if you think of hot air, right? Does it have the same density as cold air? No, the hot part of your house is probably the upstairs. So hotter things tend to be less dense. Colder things tend to be more dense. So for example, you can say, what is the density of ice? Do you think it'll be higher or lower? Yeah, exactly. It should be lower because ice floats, right? So less dense things will rise up. Yep.
So would that mean that for like humans, is that like we're technically pretty much heavier than the air, right? Like the air's like, you know what I mean? Like we're not floating or anything.
That's a good point. So if we think about us as objects, right? We have a much, much higher density than the air around us. So we sink, luckily. We don't float. However, if you take something like a helium balloon, the density of helium is actually a lot lower than the air around us, so a helium balloon will float up.
Oh, okay.
So you've got to think about it always in terms of density, not mass. It's kind of a weird thing to think about, right? Because if you think about the mass of the air on our planet, it's a huge amount of mass. You can actually weigh gases. And the mass of our atmosphere is incredible. It's why your ears pop when you go up and down mountains, right? So it's different than mass. We want to look at density. Yep, so density of ice is about 0.915 grams per milliliter. There's also some other liquids that are kind of cool. So I'll show you one.
That was 9, right? 9.1.
Yeah, unfortunately, that's my PhD handwriting. They say the longer you're in school, the worse your handwriting gets. That's why doctors have such terrible handwriting. All right, so we have this element on the periodic table called mercury. If you look at the periodic table, it has the symbol Hg. It's really weird stuff. If you look at old thermometers, it's that liquid metal inside the thermometer. So it's a very odd element because most metals are solid. This one's a liquid. The density of mercury is about 13.53 grams per milliliter. The fun thing with mercury, despite it being toxic, is if you have a bowl of mercury, you can take pennies and quarters and you can throw them in there and they'll float. It's one of the only liquids where you can throw solids in there and it will float just about anything you throw at it. So it's kind of neat. I'll see if I can post a video of that later though. But it is important to remember that density can vary widely. We have some things where the density is down to below 1 and other things that are up to about 13 to 15. Uranium is one of the most dense elements that we know of. And if you're holding uranium, it's going to feel about twice as dense as lead. So it's very, very heavy stuff. All right. Does that make sense? So in lab tomorrow, you're going to be looking at the mass of pennies, the volume of pennies, and then calculating the density of pennies, and then coming up with some hypotheses to explain what you're observing. So that's going to be your goal tomorrow. All right, so changing gears, we're going to talk about chemical properties rather than physical properties. A chemical property describes how matter reacts with other types of matter. And the easy way to remember this is, unlike physical properties, when we're looking at a chemical property, we can't see it unless we're observing a change. So the key word here is change, right? When we're looking at chemical properties, we're changing one type of matter into a new type of matter. All right, so I'll give you some examples and then we'll do some practice. So let's look at a few examples here. The first one is what happens if you expose iron to a lot of oxygen. So let's say you have a steel tool which has a lot of iron in it and you leave it outside for a really, really long time. Let's say hundreds of years. What will happen to it? Yeah. It'll rust, exactly. And the interesting thing is, when you form rust, it's actually combining the elements of iron and oxygen together, and you're making a new type of matter called iron oxide. So you're changing it. You're making and breaking bonds in that process. All right, another type could be wood. Wood is primarily made up of something called cellulose, primarily carbon, oxygen, and hydrogen. And what you can do is you can take wood, oxygen, and heat. And what do you get out if you combine all of this in your fireplace?
Fire?
Yep. You get ash and heat, right? So it doesn't all disappear. You do end up with some ash. What else do we get out?
What about carbon?
Yeah, carbon dioxide. So CO2 gets emitted when you burn something, right? So that's important to remember as well. All right, another one could be silver and oxygen. I know my grandma, every Christmas, has a few silver items that she brings out, and every year we have to polish it. Why? Tarnish, right? So you can actually get tarnish in this case. Yep.
Oh, so I have two questions. So when something rusts, is the material still there? I guess let's say you just left a piece of like a knife out like thousands of years. Does it like dissipate to the air, or does it just turn what is the?
That's a good question. So the surface layer of iron will react with the oxygen in the atmosphere and essentially coat it with rust. If you, let's say, get a piece of sandpaper and polish it for a while, you can probably get down to the steel and see clean steel again. So it really only affects the outer layer exposed to air, if that makes sense.
Okay. So is there ever a point where it just like something can be like total rust though? Couldn't it?
Yeah, so if you leave it out long enough, that will start to kind of corrode and flake off and then expose the layer underneath and so on until it completely disappears. But if you, let's say, leave a pair of trimming shears in your garden for a week, you can polish that off. Okay. So it just depends on the length of time.
Okay, sorry, I have another
question.
No,
it's fine.
So what about tarnish? Is that like how would you like describe it as a?
It's really, really similar to rust, right? So the difference with rust is a combination of oxygen and iron.
Okay.
Tarnish is a combination of oxygen and silver. So you're making silver oxide rather than iron oxide. So you're actually making and breaking bonds with silver atoms. We'll talk a lot more about bonds later, though. Okay, so those are 3 examples. I want you to help me with some of these. And I want you to help me describe if it is a chemical or a physical change. So the key thing is, are you making a new type of matter during this change? So the first one, and you don't need to answer right away, we'll maybe pause and think about these, is frying an egg. Next one is freezing water. Next one is crushing rock. Next one is digesting food. And the last one is water evaporating. Okay, so what I want you to do is think about these and then check with your neighbor and see if you agree. But ultimately, we need to determine whether or not we're changing the type of matter into a new type of matter. All right, give me a thumbs up if you think you're pretty confident. You can give me a thumbs down if you have no idea what's going on. You can give me a sideways thumb if you're a little uncertain. All right, there's some thumbs. All right, let's go through these because it is confusing. So the first one is frying an egg. Do you think that's a chemical or physical change? It's a little abstract, but do you think you're making or breaking bonds when you're frying an egg, or do you think it's still a normal egg? Another way of thinking about it is, can you unfry an egg? No, it's kind of a permanent change, right? So when you do that, it's no longer a raw egg. You've actually made new bonds that cause the egg to solidify and become hard, right? So frying an egg is an example of a chemical change. When you fry an egg, a raw egg is no longer a raw egg. It is something new entirely, right? So that's a big thing to remember. All right, what about freezing water? Physical, right? It's still water. You can unfreeze water and convert it back into a liquid. That's an easy thing to remember. All right, what about crushing rock? It's a physical change. When you crush rock, it's still rock. In fact, if you take that rock and you put it under high pressure, you can actually push it back together again into a new rock, right? So this would be a physical change. All right, what about digesting food? Chemical. It's an important chemical change. When you digest food, you're actually breaking the bonds in those food. By breaking those bonds, you're releasing energy. That's the energy we use to survive, right? So we need that energy from chemical bonds. What about water evaporating? Physical. It's still water. When water evaporates, it goes into the clouds, then it can rain, as we see most winter. So this would be an example of physical change. So like I said, the key thing is remembering whether or not things are being broken, like bonds, or made, like bonds. If all you're doing is changing the state of something, meaning from a solid to a liquid, or one size to a smaller size, that's just a physical change, right? All right, so now what we've got to do is we've got to dig in and classify matter in a bit more detail. So that's what we're going to spend the last chunk on. And this might seem like elementary school a little bit, but bear with me. There are 3 types of matter. Three main types, I should say. Does anybody remember what those are? Solid, liquid, and gas. So we've got a solid, got a liquid, and we've got a gas. There's actually one other one, it's pretty common that people don't think about, called a plasma. Has anybody heard of that? Plasma is a little bit weird. Easiest way to describe a plasma is think of a fire, right? What is a flame? What type of matter is that? Is it a gas? Well, kinda. It's a super excited gas. So a plasma is a type of gas that's heated up and acts really weird. But as far as we're concerned, we're not going to do much with fire. We're going to focus primarily on these 3 states. So the easiest way to define a solid is it retains its shape. So if I set a rock on the table, the rock isn't going to spill off the edges of the table, right? It's just going to sit there like a rock. Liquid, on the other hand, will flow and take the shape of a container. So that makes sense. We've all seen liquids like water. You can pour it in a mug, it'll fill the bottom of that mug. Gases, on the other hand, will assume the shape and volume of a container. Oops, that should be an E. So those are the three main classifications. With gas, if you have gas in a room, it'll expand and eventually disperse itself throughout the entire room. It normally doesn't settle into one specific location on the room. All right, so let's try to go even further and classify matter using a flowchart. And so we know matter can exist in three different forms: solids, liquids, and gases. However, sometimes we're dealing with pure matter, and sometimes we're dealing with impure matter. And I'll describe what that means in a bit more detail. This will be our flowchart. All right, pure matter can be split up into two different classes. First class is elements. Easy way to remember if something's an element is to look at the periodic table of elements, which most of you are familiar with in one way, shape, or form. Got a periodic table on the wall. If you see something that's made up entirely of one of those elements, it's an element, right? So an example of this that many of you might be familiar with would be something like helium. So when you fill a balloon with helium, it is just full of a bunch of helium atoms floating around. Nothing else in there besides helium, for the most part. All right? Alternatively, we can have compounds or molecules. And what these are is some sort of combination of elements. So more than one type of element bonded together. And we'll talk a lot more about what it means to be bonded to something later. All right, so if you think about water, what are the elements that make up water? Does anybody? Hydrogen and what else? And oxygen, right? So if you're familiar with that movie Waterboy, it's H2O. So what do you think H2O really means? What does that little 2 mean right here?
Two molecules of hydrogen?
Yeah, close. It means for every one oxygen element, you have 2 hydrogens involved, right? So it's a 2-to-1 ratio of hydrogen to water in order to make water. So if you take water and you can actually rip apart those atoms and break those bonds, you'll get twice as much hydrogen as you do oxygen, and we can see that experimentally. So a compound means it's not just oxygen, it's not just hydrogen, it's a combination in a 2-to-1 ratio.
Wait, does it have to be exactly 2-to-1 ratio?
Yes, exactly. So in this case, it's defined by the ratio of atoms present. Okay, does that make sense?
So then more than one type of element bonded together, but only 2 at a time? Is that?
So, no, you can have more than 2. So for example, let's say cellulose. Cellulose has a bunch of carbon, bunch of oxygen, bunch of hydrogen. It doesn't have to just be two. It could be any combination of more than one, right?
Oh, but you said that it has to be the number two. Only has to be. You're only allowed two of those little twos.
Yeah, so it's confusing. So let's say we change this to H2O2. That's not water anymore. That's hydrogen peroxide. We wouldn't want to drink hydrogen peroxide. So we have to be very, very careful as chemists, writing things out the correct way to describe the molecule that we're talking about.
Oh, so that's the molecule.
Exactly,
Oh, okay.
exactly. Where helium, if we have a balloon of helium, it's just a bunch of helium atoms, no other atoms present, right? All right, for mixtures, it gets a little bit weird. Actually, I'm going to change this to mixture. I apologize. I'm ruining everyone's notes. And what we're going to do is split this into two subclasses. We've got homogeneous. In one class, and then we've got another class called heterogeneous. All right, in a homogeneous mixture, the clue to look at is the prefix homo. What does that mean? The same. Okay, so a homogeneous mixture means it is the same throughout. Or evenly mixed. An example of this would be salt water. So if you take, let's say, a teaspoon of salt and you throw it into a liter of water, it's now a combination of salt mixed evenly with that water, right? So if you shake it up enough, that salt will completely disappear into that water. It's evenly mixed. So it's homogeneous. It's the same throughout. It doesn't matter if you get sample at the top or the bottom. It's going to be about the same, right? Yep.
Are you counting emulsions in homogeneous or heterogeneous?
So what do you mean by emulsion? I should ask that first.
Like soap and water and oil.
So let's say you take something and you mix it up to the point where it's even throughout. Some emulsions you're pulling in air, so it's not entirely even throughout, but that's getting into kind of a gray area. We'll avoid gray areas.
Of course.
All right, heterogeneous mixtures means it's different throughout. So an example I like to use is pizza. Think about pizza, one part of its crust, one part of its sauce, one part of its cheese, maybe you've got toppings. It's not mixed evenly. We've got different layers going on there, right? So that would be an example of a heterogeneous mixture of ingredients to make food. It's not the same as salt water. So in general, we're going to classify things into these 4 subcategories, and I ask you to do some of that on your problem of the day in addition to classifying matter. If you guys have questions, though, you can always email me or come by my office hours. My office hours, if you remember, are right after class. So if you do have questions about this, you can follow me to my office.